Okay, so whenever we look up, it's really easy to just think of the stars as, well, permanent fixtures, right? But the universe is incredibly dynamic. Let's dive right into this explainer and unravel the mystery of one of the most famous star clusters out there, the Hyades. We're going to see how tracking the invisible debris of this one single local cluster is, literally, reshaping our entire understanding of the Milky Way's hidden structure. Now, at just 47.5 parsecs away, which is roughly 150 light years, the Hyades is practically our cosmic next-door neighbor. And because of this extreme proximity, it's absolutely the ultimate laboratory for stellar dynamics. We aren't just looking at some fuzzy, distant blob of light here. We can track the exact positions, the precise movements of individual stars with just staggering accuracy. If you've ever glanced at the constellation Taurus, you've actually looked right at the Hyades. You probably recognize its famous foreground star, Aldebaran, shining bright in the night sky. Now sure, Aldebaran is just a line-of-sight illusion, not a true cluster member. But actual Hyades stars like Prima Hyadum, Secunda Hyadum, and Ino, they've captivated us for centuries. But for the longest time, we were totally zoomed in on this dense central core. We were completely missing the bigger picture. Because the Hyades isn't just some neat, spherical little cluster anymore. It's actively being pulled apart into a massive tidal stream. So what is that? Well, a tidal stream is exactly what it sounds like, a phase-coherent trail of stars formed by the gradual gravitational stripping of a star cluster. Essentially, as the group orbits through the Milky Way, these immense gravitational forces are stretching it out, literally tearing stars away from the main pack and leaving behind this huge trail of cosmic debris. And thanks to the completely unprecedented precision of the Gaia spacecraft, we can finally map out this destruction in real time. When we analyze the preceding tail of the Hyades, we see stars that have been stripped away and are now just running ahead of the main cluster. I mean, this structure extends an astonishing 170 parsecs forward and contains nearly 300 stars stretching way out into space. It's huge. Then there's the other half of the story, the following tail. This one is a much more shredded, kind of chaotic structure. We're talking over 230 stars, trailing up to 70 parsecs behind the main cluster, scattered out like cosmic breadcrumbs. So this 650-million-year-old cluster is quite literally disintegrating right before our eyes, leaving this massive, stretched-out footprint all across our local galactic neighborhood. Now, this discovery actually fueled a really fierce debate among astronomers for years. Is this extended stream just an evaporated cluster? Stars that just naturally drifted away over time because of internal dynamics? Or, and this is the wilder theory, are these actually field stars that got hijacked and trapped by a resonant intrusion, like a powerful gravitational ripple echoing out from deep within our galactic disk? To solve this, scientists turned to velocity maps, specifically the UV plane, to track exactly how these stars are moving. And by analyzing the mass and the chemical makeup of the data representing the Hyades stream, they found a massive clue. The stream perfectly matches the signature of typical random field disk stars. It doesn't have that unique chemical fingerprint of stars born together in the original cluster. That right there, that was the smoking gun pointing directly toward the resonant origin theory. So that brings us to the absolutely crucial question. If the cluster core is sitting right here, but its stars are stretching hundreds of parsecs out into the void, and the surrounding stream is just full of trapped field stars, what invisible galactic forces are tearing it up? What's creating these massive resonances? We know for sure it's not random. Something incredibly powerful and highly structured is acting on our neighbor. Well, the culprit, as it turns out, is the Milky Way's rotating central bar. Our galaxy, you see, isn't just a simple spiral. It has this massive, elongated bar of stars right across its center that rotates like a giant propeller. And as it spins, it sends these sweeping, powerful gravitational waves out through the galactic disk. Those waves, they crash right into open clusters like the Hyades. To figure out exactly how this bar operates, scientists ran some pretty intense N-body computer simulations, basically pitting different models against each other. They tested a fast bar, which spins at about 55 kilometers per second per kiloparsec, against a slow bar, spinning around 40 to 45. The whole goal was to see which virtual galaxy would tear the virtual Hyades apart in a way that actually matched Gaia's real-world data. And the results were completely definitive. The slow bar wins hands down. A Milky Way bar rotating at roughly 40 to 45 kilometers per second per kiloparsec perfectly, perfectly, replicates the exact tidal tails we observe today. The fast bar models, they completely failed to match the observed density structure. Just think about that for a second. We are literally using the localized destruction of the Hyades to measure the spin rate of our entire galaxy's core. That is mind-blowing. However, science is rarely without its hurdles. And this explainer wouldn't be complete without addressing a major complication: contamination. Remember those field stars we talked about? Well, background galactic disk stars can easily mimic the kinematics, the physical movements of the Hyades stream. Especially when we're looking out 150 to 300 parsecs away from the core, it becomes incredibly difficult to tell a true stripped Hyades member apart from just some random background star passing through. We need a solid way to positively ID the real deal. To fix this, astronomers have to act a bit like cosmic detectives. Using follow-up observations from instruments like WEAVE, they're targeting those distant stream stars to look specifically at their lithium abundance. You see, stars born in the Hyades have a very strict, highly unique lithium-to-temperature relation. By checking this chemical makeup, scientists can essentially run a cosmic DNA test. This lets them weed out the galactic imposters and confirm exactly which stars belong to the true tidal tails. Honestly, this entire discovery completely changes how we view the night sky. The Hyades is no longer just some pretty cluster of stars to look at through binoculars. It is a dynamic, living instrument. By simply tracking the debris of local star clusters, we're actually weighing and measuring the massive, invisible dynamics of our entire galaxy. It really makes you wonder, as our instruments get even better, what other local star streams are out there, quietly hiding invisible secrets about the grand structure of our Milky Way.